So next up is field size. So when we're talking about field size, we're talking about the amount of tissue and the area that we actually irradiate, and that's primarily controlled by your collimation. We'll talk about different types of field size limiters, but mainly what you're going to be dealing with is what we call aperture diaphragm, which is your collimators. Variable aperture diaphragm, which is your collimator. So do changes in field size necessitate changes in X-ray production is what we'll talk about. What technical factors should we be using to make those changes in X-ray production? We'll answer that question. We'll answer, do changes in field size affect penetration? We'll answer whether or not changes in field size affect patient dose. And we'll also talk about how changes in field size affect occupational dose, if they do. So how do changes in field size affect scatter creation? What are the options for limiting field size? And how does scatter affect image contrast? And finally, how does scatter affect image receptor exposure? So beam limitation, when we're talking about beam limitation, we're talking about primarily collimation, and that is controlled on your housing. And if you're looking at this graphic, and it can be found on page 189 of your textbook, again, refer you back to last semester when we were talking about, it's the first section of last semester, where William Rollins invented collimation or field size limitation whenever he put lead inside of the leather strips. And he was the dentist who sought to only expose the portion of the patient that he was interested in seeing, and that being the patient's mouth. He was a dentist. So his purpose was in a reduction of patient dose. Instead of blasting the patient's entire head, the only thing that he wanted to expose was the mouth. So his goal was patient dose, reduction of patient dose, but we've seen other benefits to it as well. It's really kind of common sense. It all ties in together. If you limit the exposure area to just what you need to see, then you limit all of the interactions that would be created outside of that area. Well, what are the interactions? You got 4 of them. You got absorption, which is all about patient dose. You got transmission, which you've transmitted X-rays through tissue type that you don't even need to see, so the results on your image are densities that you don't need to see. But more significantly, you're going to create scatter radiation in those tissues that you don't need to see, that are going to be projected onto the image, the portion of the image you do need to see. So there's a lot of benefits to beam limitation. You collimate and you save patient dose. You collimate and you eliminate scatter. You eliminate scatter, you increase your visibility of recorded detail, and you increase your contrast. So the only time beam limitation is detrimental is if you overdo it. If you increase your collimation to a point where you collimate off anatomy of interest from the image and you have to repeat the image, then collimation is detrimental. But aside from that one time, collimation is always a good thing, providing you can see the anatomy that you need to see. So beam restrictors purposes, primary purpose was dose, but secondary to that we see an increase, an improvement in image quality. And that's all about visibility of recorded detail. The only way beam restriction inhibits sharpness of recorded detail is if you just collimate the image off, or the anatomy off, and then you have no sharpness of recorded detail. So beam restriction, collimation, is all about visibility of recorded detail. It improves contrast, shortens the grayscale. Now we're getting into what you might want to equate with tissue thickness in density and beam restriction. We prevent some scatter from being created whenever we beam restrict. So since we prevent that scatter from being created, we prevent what would be created from penetrating through and exposing the image receptor, and therefore we lose density. So going back to our explanation on the way the phototimers work, can the phototimer differentiate between penetration and scatter? And the answer is no. So if our phototimers are set to create a image or a density and an image based on how much is penetrated through the patient, that scatter is accounted for in that number. So if you collimate, you're going to remove some of those numbers. And removing some of those numbers, if your mass is not adjusted, then your density comes out too light. Okay, so I just kind of made a shift there from exposing, utilizing automatic exposure to a set technique. So if you set a technique and you don't adjust your mass, then your image is going to come out too light. If you collimate while you're phototiming, then your phototimer is going to be starved of those scattered photons, but it's not going to terminate the exposure until it receives enough radiation. So it will automatically adjust your mass whenever you're phototiming to get you to the right exposure on your image receptor. So again, image quality, sharpness of recorded detail, beam restrictors, providing you don't collimate off the anatomy of interest. Beam restrictors have no effect on sharpness or recorded detail. It's all about visibility because it helps to improve your contrast. Unfortunately, if you don't change your technique, your density is going to suffer and you're going to have to adjust for your collimation. The adjustment's not going to be significant. It's not even going to be a doubling of your mass. Again, when you get into clinicals, play around with your collimators. Look at your, find something, build a, air quotation, patient out of things like saline bottles. Shoot through saline bottles with your collimators wide open. Use the same technique but collimate down to a very small area. Compare the index number between those two. They'll be totally different. And then do the same thing, only put your saline bottles on top of a automatic exposure and make exposures on that. Lay out maybe 4 or 5 saline bottles side by side and make an exposure with your collimators wide open, phototiming, and then collimate down to a small area and watch what happens to your technique between those two exposures. And you'll see how the collimators work in relationship to the scatter radiation that's created and projected down onto the automatic exposures. So we've got multiple types of beam restrictors. We've got what you're most familiar with, and that is your collimator, and technically is called a variable aperture diaphragm. You might see some questions asking about positive beam limitation. PBLs aren't really used that much anymore. I'll tell you kind of the history of PBLs. That's positive beam limitation, and what that is automatic collimation. So back in the early days of X-ray imaging, when we didn't really understand radiation exposure and how harmful it could be, there was no such thing as collimation, really. In a few cases like Rollins and some other places, there might have been some collimation, but for the most part, we didn't understand X-ray exposure all that well. So there was no collimation. It wasn't until people started suffering from radiation burns that more radiation safety devices were put into place, including collimators. So some of your older techs at that time didn't utilize the collimators nearly as much as what they should have. So let's say you're shooting chest X-ray, there's never a reason to have a field size larger than the image receptor size. So let's say we're shooting chest X-ray, And the image receptor is 14 inches in one dimension by 17 inches in the opposite dimension. If somebody's got a collimated field that goes from the top of your head down to your waist, that's all unnecessary exposure to the patient. But yet people were doing that. So federal regulations required new manufacturers of equipment to put into place automatic collimation. So the machine would detect the size of the image receptor that you put into the wall bucky or into the table bucky, and the collimators would adjust to that image receptor size. So if you put a 14 by 17 into the bucky, your field size was going to be 14 by 17. If you put a 10 by 12 in, it was going to adjust to 10 by 12. That's positive beam limitation. Now with our image receptor sizes being really pretty much all the same size, it's 17 by 17 or 16 by 16, positive beam limitation, it might still be present in that it would limit it to no larger than that image receptor size, but it can't determine exactly how big your radiation field should be for the anatomy that you're interested in seeing. So it's not going to automatically collimate for KUB or a chest x-ray or anything like that. So PBLs, you might still run into a PBL if you happen to be working in a clinic that uses individual image receptor sizes if they have not converted from CR to DR, but you may never in your career work with PBLs. But again, it may still be a question you're required to answer. An aperture diaphragm is a diaphragm that you would add after your collimator housing. So if you look on page 192 of your textbook, you see a couple of different things. You see a tube housing or a collimator housing, you see a cylinder, and you see a diaphragm. The aperture diaphragm is a fixed opening in a piece of usually lead or lead impregnated material that would absorb and act as a collimator, but it's not adjustable. Okay, so variable aperture diaphragm is what you use in a collimator housing. You can adjust it. An aperture diaphragm is just a static hole in some sort of absorber. That's basically what Rollins used. And then cylinder cones can be of a couple of different variations, and if you look on page 193, you'll see those variations. It can truly be a cylinder, or it can be a conical in shape, like what you're seeing in figure 11-14. So they're like three-dimensional collimators. They extend out almost to skin level in a lot of cases, so that they can prevent off-focus radiation. They can from messing up your sharpness of recorded detail, and they can collimate all the way down to the skin area. You just don't see those a whole lot anymore either. So aperture diaphragms, you don't see a whole lot. Cylinder cones, you just don't see a whole lot, but they're still out there. We used to use cylinder cones quite a bit for exams like sinuses. So field size, how does it affect patient dose? Increased collimation means decreased field size. So if you increase your collimation, that means you make the field size smaller. If you make the field size smaller, then you don't irradiate anatomy that doesn't need to be irradiated. So your patient dose goes down. Likewise, if you increase collimation, you make your field size smaller, and you prevent the scatter that would be created in that area with the field size open. If you close it down, then the area that is no longer going to be exposed won't cast scatter radiation over the anatomy of interest. So your contrast improves. Anytime you remove scatter, contrast improves. Grayscale shortens, density decreases, sharpness remains unaffected. and visibility, because contrast is improved and grayscale is shortened, visibility improves as well. So increasing field size increases the number of photons in the primary beam, which increases the amount of tissue being irradiated. It increases the number of possible interactions, but the PEs still won't reach the film, so they don't affect anything. But the scatter radiation does. Since the scatter radiation reaches the image receptor, it spreads a layer of fog across the image. Across the image, reducing the contrast and increasing the density, leading to less visibility or recorded details. So what we're talking about here is increasing the field size, which means decreasing collimation. Increasing the field size decreases collimation. That's bad. Increasing collimation means decreasing the field size, and that is good. So diaphragms and cones. A diaphragm is a single sheet of lead with a hole in it. It can increase penumbra issues, so you can actually reduce sharpness of recorded detail with diaphragms and cones. And again, we've got cylinder cones, we've got extension cones, and in the case of the cones, because they're three-dimensional, they can absorb some of the off-focus radiation and reduce the penumbra that might be visible with the diaphragm. One thing that I need to point out is in your variable aperture diaphragm, that's your collimation, there are two sets of collimators. And when I say two sets of collimators, I'm not talking about the collimators that you see. You see two collimators. You see collimators that shutter your field size from both lateral sides from left to right, and one from top to bottom. That's not what I'm talking about. That's one set of collimators. Okay, there's two sets of shutters, one set of collimators. So all of these down here, all four of these collimators, all four of these shutters account for one set of collimators. What I'm talking about in two sets of collimators is this up here is also a collimator. If you could remove your collimator housing, if again you look on page 192, you see the collimator housing without all these squiggly lines from the focal spot. And you can see that cone looking thing on top. So basically what you've got is a multi-leaf collimator. And I can't really describe this all that well, but it's kind of like a cone that adjusts inward and outward. And the purpose for that is between this collimator and this collimator, you can reduce the amount of off-focus radiation. So if you've got off-focus radiation that bounces from up here, then chances are it's going to absorb in this first set of collimators along with all this other portion of the beam that we don't necessarily want. So this is round, and then these are the collimators that you're more familiar with. I'm sorry, these are the collimators you're more familiar with. These are the ones, and you control both of them. Whenever you open and close your collimation, you actually open and close this, and you open and close this, but this is what you see. Because this is going to be on the upper end, the top of the x-ray tube, behind the mirror. You're not going to see this unless Biomed comes in and removes the collimator housing. So again, the purpose for both sets of collimators, and that's not two sets of shutters down here, the purpose for this set of collimators on the bottom, the shutters you see, and the multi-leaf collimator you don't see, is to limit off-focus radiation. Further, if you use extension cones and cylinders, it further reduces the likelihood that we'll see off-focus radiation on our image, and therefore it improves penumbra. Or it improves umbra. It reduces penumbra. So your collimators, variable aperture diaphragm, there are two sets of shutters. It's to reduce off-focus radiation, which reduces the penumbra. Positive beam limitation we talked about. Field size should never be larger than the anatomy of interest. But the field size should never be larger than the image receptor, but it should be determined by the anatomy of interest. What I mean by that is if you're taking a chest x-ray on a patient and you're utilizing a 14 by 17 image receptor, your field size should never be larger than that 14 by 17 image receptor, because you can't capture any anatomy outside of that 14 by 17 area. But if you're taking an x-ray on a 10-year-old child on a 14 by 17, you should not be using that entire 14 by 17. So the field size should never be larger than the image receptor, and it really should never be larger than the anatomy of interest. So absolutely never larger than the image receptor. But even if the image receptor is larger than the anatomy of interest, then the anatomy of interest should determine your field size. To calculate projected field size, what you're setting up is basically what we call a ratio type problem. And a ratio is the ratio between the source to the diaphragm distance, that is the SDD that you see on page 192. We're comparing that to the source to image distance, and then we're comparing the opening size to the projected field size. So in a ratio type problem, as long as you set up your variables so that you're comparing the same things across from each other, then it doesn't matter which one you put on top and which one you put on bottom. So what I recommend that you do is get familiar with the formula and refer to it as big over big is equal to little over little. So you've got two big things and you got two little things. So your big things are going to be your SID. So looking at your SDD compared to your SID, SID obviously is far larger than your source to diaphragm distance. And now look at the differences between your field size. Which one is smaller and which one is larger, or your radiation field. The opening in the diaphragm is going to be significantly smaller than the projected field size on the image receptor. So your big measurements are your SID and your field size at the image receptor. Your little distances or your little variables are going to be your source to diaphragm distance and the diaphragm opening size. So in this example here, you've got a 10 by 4 diaphragm is placed 5 inches below the target at a 40-inch SID. So what is the field size? So how you would set that up is you'd have to calculate it in two different dimensions because it's rectangular. So you got a 10-inch distance in one dimension, a 4-inch distance in the opposite dimension. So your big would be 40 inches, 40-inch distance, and your unknown would be your field size, because that's what it's asking you, what's the field size. So it'd be 40 over x is equal to our distance between our target and the diaphragm opening is 5. Okay, so we got both of our vertical distances on top. So we're comparing SID to SDD. All right, so both of those need to be on top. So it'd be 40 over x is equal to 5 over 10. So how you would solve that is to cross multiply. So it'd be 40 times 10 is 400 is equal to 5 times x is 5x. And now you divide by 5 both sides. X would be 80. So field size in one dimension would be 80. You set it back up exactly like you did before. and you would divide 40 over x is equal to 5 over 4 in this case, because your target to your diaphragm distance in this dimension is only 4 inches. So it would be 40 over x is equal to 5 over 4. So cross multiply, and you got 40 times 4, and that'd be 160 is equal to 5x. Divide 160 by 5, so you'd have 32 is equal to x. You have a massive field size of 80 inches in one dimension times 32 inches in the opposite dimension. So if I get back into the classroom and I can kind of work through this on the board, I will. I can't guarantee that, but you can work through some of the problems again on in your DeAngelis. And just remember, you got to compare. You got to put the same things as numerator as what you put as denominators. So these distances on top need to be comparable to each other. In this case, we went vertical distances here, and we went horizontal distances there. Now you could flip that whole thing over, and if you get a little bit confused on the test as to which big comes first, just make sure that you keep the same big on top as what you have the little on top. And what I mean by that is, if you flip this around and you make your field size on top, so it would be x over 40 is equal to, well, now you got to compare this again to this, so it would be 10 over 5. And once you cross multiply, you're going to come out with the exact same answer. So it doesn't really matter which way you set it up, as long as you keep the right things on top. Make sure this is the same relative type of distance as this, and this is the same as that, and you should be fine.